This is Lab 5, Choose Your Own Adventure. First we will be introduced to the adventure, then an experimental model and its plotted positions will be shown in Tracker. Then we will go through the samples of the code in Python and their respective physics concepts. Finally, we will compare and contrast the experimental and computational models in terms of drag and energy. Then we will think critically. This lab is labeled Drag Force and Energy. In the lab, a ball is pushed off a ledge. With that, the ball experiences the effects of gravitational and drag force. The purpose of this lab is to view the changes in energies for when there is not and when there is drag force in system. This lab combines labs 2 and 4. Some main principles found in this lab are Newton's second law, or the momentum principle, and the conservation of energy. The result of this lab shows that the ball accelerates at a rate inversely proportional to its mass, moving in the negative y direction. The system satisfies the energy principle, and the computational model with drag proves to be a better representation of the experimental model and Tracker. Here is the video of the ball being dropped from a ledge and the corresponding graph using point mass. The parameters in the experimental model are time and xy positions, giving velocity by the slope of the graph. Measurements were calibrated by the distance of the drop, which was 1.397 meters. The first point mass coordinate is negative 0.004, negative 0.004 meters, which is inputted when the code is initialized. The plotted graph from the experimental model first shows a small plateau, then sharply dips down, almost looking like a linear constant slope towards the end of the drop. This is a quadratic curve. The code is first initialized using the ball.m variable, setting the mass of the ball to be 0.425 kilograms. The ball.pos variable is set to be the vector negative 0.004, negative 0.0040 meters, because that is the first point mass in the Tracker. Since the ball begins to fall from rest, the ball.vel variable is set to be 000 meters per second. The time step is set to be 0.021 seconds, and the gravitational constant g is the constant 9.8 meters per second squared. The j-hat vector, which will be used for scaling later, is set to be the vector 0, 1, 0, and the proportionality constant b is experimentally determined to be 0.02868, which will be used in the equation for f-drag later on. System energies are then initialized using the conservation of energy equation. Delta E equals delta U plus delta K. K-trans, or the translational kinetic energy, is defined to be 1/2 mv squared. The same equation is directly inputted into the code as is UG, the gravitational potential energy, mgh. After the energies are inputted for later use, a CSV output file is coded to plot the time and position in a CSV file named pythontest.csv. The calculation loop is set for 0.543 seconds, and in this, the energies are initialized from before to be set as K-trans and UG. Then the line ball.vel equals ball.vel plus fnet over ball.m times delta t is found by the initial equation, F equals ma, from Newton's second law. This equation is derived from the motion prediction of velocity. For the motion prediction of distance is denoted by ball.pos equals ball.pos plus ball.vel times delta t for the same derivation. Then, to calculate the net force, Fnet, you must sum Fgrav and Fdrag. Fgrav is denoted by negative mg. In this case, we will set Fdrag to be the vector 0, 0, 0 for comparison purposes. Delta is defined as final minus initial. With this, delta K-trans is found by subtracting the initial K-trans from the final, and the same for delta UG. Now, when the code is run, the diagram on the right shows Fgrav represented by the yellow arrow and Fdrag, or the lack of, represented by the blue arrow. We then plot delta K-trans represented by blue, delta UG represented by red, and the sum of the energies delta K-trans plus delta UG represented by green. With the lack of drag force, delta K-trans and delta UG are linear, and as delta K-trans increases because the ball is falling, delta UG decreases. This follows through with the conservation of energy because kinetic and potential energy have an inverse relationship. As one increases, the other decreases, and vice versa. Now we will add in the drag force represented by negative b times the magnitude of ball.vel times ball.vel. This will show the true motion of the ball, which will be discussed later. Now, when the code is run, a small blue arrow pointing upwards is present, representing the drag force. This is much smaller than the weight force because of the relatively heavy weight of the ball. Delta K-trans, delta UG, and the sum of the energies are still plotted on the graph on the right, but this time they are curved. The curved area accounts for the drag force and the bump in the quadratic graph that was shown earlier in the model for Tracker. The computational model with drag force is obviously the more proper indicator of the experimental data. They follow the same path very closely and is a similar shape to what was in tracker. Now we can look at the energies. Due to the conservation of momentum, when kinetic energy increases, the potential energy decreases. This correlates with the correct theory. Now, what if the ball was initially thrown off the ledge rather than slightly pushed? In order to show this case, the ball depth L variable must be changed to the vector 0, -5, 0 to show an initially downwards throw. When the code is run, this model shows the weight force is much larger because the ball was thrown. The drag force appears immediately rather than after some time, and the energies do not start from 0 because the initial velocity is no longer 0 meters per second squared. Thanks for watching.